Hello there, and welcome to Sleep Knowledge. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and cosmic mysteries rather than counting sheep. Either way, tonight's journey is for you. We're exploring black holes, those enigmatic voids where the universe folds in on itself in ways that challenge everything we think we know about reality. If these calm explorations help you unwind, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. Now, let yourself settle, take a deep breath, and let's begin. Black holes are among the strangest objects in the universe. They're regions of space where gravity has become so intense that nothing, not even light itself, can escape. To understand what that means, imagine a place where the normal rules of physics bend and break, where time itself slows to a crawl, and where matter is compressed into impossibly small points. The story of black holes begins with stars. Every star you see in the night sky is a delicate balance between two forces. Gravity pulls inward, trying to collapse the star. Nuclear fusion in the core pushes outward, resisting that collapse. For millions or billions of years, these forces remain in equilibrium, and the star shines steadily. But all stars eventually run out of fuel. When a massive star, one at least 8 times the mass of our Sun, exhausts its nuclear fuel, that outward pressure disappears. Gravity wins. The core collapses in on itself in a fraction of a second. What happens next is difficult to comprehend. The collapse triggers a supernova, one of the most violent explosions in the universe. The outer layers of the star are blown into space at tremendous speeds, creating brilliant nebulae that can outshine entire galaxies for weeks. But the core continues to collapse. If the remaining core is massive enough, nothing can stop it. No known force in nature can resist the crush of gravity. The core compresses beyond the density of atomic nuclei, beyond the density of neutron stars, into something else entirely. It becomes a black hole. Let's pause for a moment and consider what density means in this context. A teaspoon of neutron star material would weigh about 1 billion tons. That's already beyond our everyday comprehension. But a black hole takes this further. All the mass of that collapsed core gets compressed into a point of infinite density called a singularity. At least, that's what our current mathematics tells us. The singularity is surrounded by an invisible boundary called the event horizon. This is the point of no return. Anything that crosses the event horizon, whether it's a particle of dust, a planet, or a beam of light, can never escape. The event horizon isn't a physical surface. You couldn't stand on it or touch it. It's simply the boundary beyond which escape becomes impossible. The size of the event horizon depends on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. For a black hole with 10 times the Sun's mass, the radius would be about 30 kilometers. Despite containing enormous amounts of matter, black holes are surprisingly compact. Now, here's where things become truly strange. Time itself behaves differently near a black hole. According to Einstein's theory of general relativity, gravity doesn't just pull on objects, it warps the fabric of space and time. Imagine you're watching a clock fall toward a black hole. As it approaches the event horizon, you would see the clock tick more and more slowly. At the event horizon itself, time would appear to stop completely from your perspective. The clock would seem frozen there forever, even though from the clock's perspective, it crosses the event horizon and continues falling in just fractions of a second. This time dilation effect is real and measurable. Clocks at different altitudes on Earth tick at slightly different rates because of Earth's gravity. Near a black hole, this effect becomes extreme. If you could somehow survive falling toward a black hole, you would experience something called Spaghettification. It's a playful name for a violent process. As you fell feet first, the gravity pulling on your feet would be stronger than the gravity pulling on your head because your feet are closer to the black hole. This difference would stretch you vertically. At the same time, gravity would compress you from the sides. You'd be stretched into a long, thin strand, like a piece of spaghetti. For smaller black holes, this would happen far outside the event horizon. For supermassive black holes, you might pass through the event horizon before the tidal forces became lethal. Not all black holes form from dying stars. At the centers of most galaxies, including our own Milky Way, lurk supermassive black holes containing millions or billions of times the mass of the Sunday. We're not entirely sure how these giants formed. One theory suggests they grew from smaller black holes that merged together over billions of years. Another proposes they formed directly in the early universe from the collapse of enormous gas clouds. Perhaps both processes contributed. The supermassive black hole at the center of the Milky Way is called Sagittarius A. It contains about 4 million solar masses compressed into a region smaller than Mercury's orbit around the Sunday. Despite its enormous mass, it's relatively quiet right now, not actively consuming much material. But supermassive black holes can be anything but quiet. When gas and dust fall toward a supermassive black hole, the material forms an accretion disk, a swirling vortex of matter spiraling inward. Friction heats this disk to millions of degrees, causing it to emit enormous amounts of radiation. These active galactic nuclei can outshine all the stars in their host galaxy combined. Some launch jets of matter and energy that extend for thousands of light years into space, traveling at nearly the speed of light. The energy powering these jets comes from the gravitational potential energy of matter falling toward the black hole. Quasars are among the brightest objects in the universe, powered by supermassive black holes consuming matter at prodigious rates. The most distant quasars we've observed existed when the universe was less than 1 billion years old. Their existence tells us that supermassive black holes formed surprisingly early in cosmic history. Let's drift to a question that puzzled scientists for decades. If black holes trap everything, including light, how can we possibly observe them? We can't see the black hole itself, but we can detect its effects on surrounding matter. When a black hole is part of a binary system with a normal star, it can pull gas from its companion. This gas heats up as it spirals inward, emitting X-rays that we can detect from Earth. By studying how the visible star orbits, we can infer the presence and mass of the invisible companion. In recent years, we've developed even more direct ways to observe black holes. In 2015, scientists detected gravitational waves for the first time. These ripples in space-time were created by two black holes spiraling together and merging into one. The collision released more energy in a fraction of a second than all the stars in the observable universe emit in the same time. Gravitational waves travel at the speed of light, carrying information about the most violent events in the cosmos. Since that first detection, we've observed dozens of black hole mergers. Each one teaches us something new about how black holes form, evolve, and interact. In 2019, scientists revealed the first actual image of a black hole. Using a network of radio telescopes spread across the Earth, working together as a single virtual telescope the size of the planet, they captured the shadow of the supermassive black hole in the galaxy M87. The image shows a dark circle, the black hole's shadow, surrounded by a bright ring of glowing gas. It's not much to look at in an artistic sense, but scientifically, it's profound. It's visual proof that these objects Einstein predicted a century ago really exist, and they behave just as his equations suggested they would. That black hole in M87 is staggeringly massive. It contains about 6.5 billion times the mass of the Sunday. Its event horizon has a diameter larger than our entire solar system, and yet it's compacted into a region where the density defies comprehension. Now, let's consider what happens to information that falls into a black hole. This question has sparked one of the biggest debates in modern physics. According to quantum mechanics, information cannot be destroyed. It can be scrambled or hidden, but it must persist in some form. But when something falls into a black hole, it seems to disappear forever, beyond the event horizon. From the outside, we can measure the black hole's mass, electric charge, and spin. But all other information about what fell in appears to be lost. This contradiction is called the black hole information paradox. Stephen Hawking spent much of his career thinking about black holes. In the 1,970 seconds, he made a startling discovery. Black holes aren't completely black. They emit radiation. This Hawking radiation arises from quantum effects near the event horizon. In the quantum realm, pairs of particles and antiparticles constantly pop into existence and immediately annihilate each other. Near a black hole's event horizon, one particle might fall in while the other escapes. From the outside, it looks like the black hole is emitting radiation. This radiation carries energy away, which means the black hole gradually loses mass. Over unimaginably long timescales, a black hole could evaporate completely through this process. For stellar mass black holes, the time required for complete evaporation is vastly longer than the current age of the universe. We're talking about 10 to the power of 67 years or more. For supermassive black holes, the time scales are even more extreme, but in principle, black holes are not eternal. The discovery of Hawking radiation raised a profound question. If a black hole evaporates completely, what happens to the information that fell in? Does it disappear, violating quantum mechanics? Or is it somehow encoded in the radiation in ways we don't yet understand? This question remains unresolved, driving some of the deepest thinking in theoretical physics. There are different types of black holes beyond the ones formed from dying stars. Primordial black holes might have formed in the extremely hot, dense conditions of the early universe. These could range in mass from tiny, microscopic black holes to ones more massive than the Sunday. If they exist, primordial black holes could make up some or all of the mysterious dark matter that dominates the universe's mass. This remains speculative, but it's an active area of research. Intermediate mass black holes would fall between stellar and supermassive black holes, containing hundreds to thousands of solar masses. Evidence for these has been harder to find, but recent observations suggest they might exist in dense star clusters. The spin of a black hole affects the space around it in fascinating ways. A rotating black hole drags space-time along with it, creating what's called frame dragging. Near the event horizon of a rapidly spinning black hole, space-time itself rotates so strongly that nothing can remain stationary. Everything gets swept along in the direction of rotation. The fastest spinning black holes rotate at nearly the maximum rate possible, completing a full rotation in just milliseconds despite their enormous size. The black hole in M87 that we imaged rotates at a significant fraction of this maximum speed. Black holes can also have electric charge, though most are probably electrically neutral. If a charged black hole existed, its event horizon would be surrounded by regions of altered spacetime different from an uncharged black hole. These solutions to Einstein's equations, called Reissner-Nordström black holes, are mathematically fascinating even if they're rare in nature. Let's drift to the question of what lies at the center of a black hole. Our current theories predict a singularity, a point where density becomes infinite and space-time curvature becomes infinite. But most physicists suspect this is where general relativity breaks down. At the quantum scale, the smoothness of space-time that Einstein's theory assumes probably gives way to something else. A complete theory of quantum gravity, which we don't yet have, would likely replace the singularity with something finite but strange beyond our current imagination. Several candidates for quantum gravity exist, including string theory and loop quantum gravity. These theories suggest that at the Planck scale, about 10 to the negative 35 meters, space-time itself becomes granular or foam-like. The singularity might be replaced by a region of extreme but finite density. We may never be able to observe what happens inside a black hole directly. The event horizon ensures that information from inside can never reach us. This means testing theories about black hole interiors is extraordinarily difficult. We must rely on mathematical consistency and indirect evidence. Some theories propose that the interior of a black hole could connect to another region of spacetime through a wormhole. These Einstein-Rosen bridges are solutions to the equations of general relativity, but they're highly unstable. Any matter trying to pass through would cause the wormhole to collapse. They remain firmly in the realm of speculation. Black holes play a crucial role in galaxy formation and evolution. The supermassive black holes at galactic centers influence how galaxies grow. When they're actively feeding and launching jets, they can heat the surrounding gas, preventing it from cooling and forming new stars. This feedback regulates star formation across the galaxy. Without it, galaxies might form stars far more rapidly, exhausting their gas supply quickly and looking very different from the galaxies we observe today. There's a relationship between the mass of a galaxy's central supermassive black hole and properties of the galaxy itself, like the velocity dispersion of stars in its central bulge. This suggests that galaxies and their black holes grow together, influencing each other's development. Now, imagine two black holes orbiting each other. As they spiral inward, they emit gravitational waves that carry energy and angular momentum away from the system. This causes the orbit to decay, bringing the black holes closer together. The inspiral accelerates. The black holes orbit faster and faster, emitting stronger gravitational waves. In the final fraction of a second, they're orbiting each other hundreds of times per second. Then they merge. The collision creates a new black hole, often with significant spin. The merger also releases a tremendous amount of energy in gravitational waves. For that brief moment, the power output in gravitational waves exceeds the combined light output of all the stars in the observable universe. The gravitational wave signal from such a merger sweeps upward in frequency and amplitude, creating what scientists call a chirp. By analyzing this chirp, we can determine the masses of the original black holes, their spins, their distance from Earth, and properties of the final merged black hole. These observations have revealed that black holes more massive than we expected from stellar evolution exist. Some of the black holes detected through gravitational waves have masses of 30, 40, or even 60 solar masses. This was surprising because stars that massive were thought to lose much of their mass before collapsing. One explanation is that these black holes form from stars with low metallicity, containing fewer elements heavier than hydrogen and helium. Such stars lose less mass through stellar winds and can produce more massive black holes when they collapse. Another possibility is that some of these black holes formed from the merger of earlier generations of black holes. A hierarchy of mergers could build up increasingly massive black holes over cosmic time. Let's consider what would happen to Earth if a black hole passed through our solar system. This is extremely unlikely, but it's an interesting thought experiment. If a stellar mass black hole passed near Earth, its gravity would disrupt the orbits of the planets. Depending on the black hole's trajectory and speed, it might eject planets from the solar system, send them spiraling into the sun, or cause collisions between planets. Earth's orbit could be drastically altered, either throwing us into a freezing elliptical orbit or pulling us closer to the sunday. If Earth came very close to a black hole, tidal forces would tear the planet apart long before we reached the event horizon. The side facing the black hole would experience stronger gravity than the far side, stretching Earth like taffy. Fortunately, black holes are extremely rare compared to stars. The nearest known black hole to Earth is several thousand light years away, far too distant to pose any threat. And black holes don't wander through space, randomly sucking up everything. They orbit within galaxies, just like stars do. In fact, despite their reputation, black holes are quite easy to avoid. They only capture matter that comes very close, If the sun were suddenly replaced by a black hole of the same mass, which it isn't massive enough to become, Earth's orbit wouldn't change. We'd freeze without the sun's heat, but we wouldn't be pulled in. The event horizon of such a solar mass black hole would be only 3 kilometers across. You'd have to get very close indeed to fall in. From a distance, its gravitational influence would be identical to the sun's. Black holes have captured human imagination in ways few astronomical objects have. They appear in science fiction as portals to other dimensions, as engines of destruction, as sources of limitless energy. While most of these depictions are fanciful, they're grounded in a kernel of truth. Black holes are genuinely exotic. The physicist John Wheeler coined the term black hole in 1967, though the concept is older. Before that, they were called collapsed stars or frozen stars. Wheeler's catchy name helped popularize these objects and sparked public fascination that continues today. Let's drift to the supermassive black hole at the center of our own galaxy. Sagittarius A star sits about 26,000 light-years from Earth. We can't see it directly in visible light because dust and gas block our view, but radio waves and X-rays can penetrate this veil. Astronomers have tracked stars orbiting Sagittarius A star for decades. One star, called S2, completes an orbit every 16 years. At its closest approach, it reaches speeds of about 3% the speed of light. These observations let us measure the black hole's mass very precisely. The orbit of S2 also provides tests of general relativity and strong gravitational fields. Measurements have confirmed relativistic effects like the precession of the orbit, matching Einstein's predictions with remarkable accuracy. Despite containing millions of times the sun's mass, Sagittarius A star is currently quiet. It doesn't emit much radiation compared to the active galactic nuclei we see in other galaxies. Occasionally, it flares briefly as a bit of gas falls in, but most of the time it's relatively dormant. This suggests that the supply of matter near the black hole is limited right now. The region immediately around it is relatively empty. But billions of years from now, when the Milky Way collides with the Andromeda galaxy, conditions might change dramatically. That collision, which will begin in about 4 billion years, will disrupt both galaxies. Gas clouds will collide and compress, triggering bursts of star formation. The two supermassive black holes, one from each galaxy, will eventually sink to the center of the merged galaxy. They'll form a binary supermassive black hole system, orbiting each other over millions of years. Gravitational wave emission will cause their orbit to decay. Eventually, they'll merge into a single, even more massive black hole. This merger will release gravitational waves far more powerful than those from stellar mass black hole mergers. By that time, the sun will be nearing the end of its life anyway, expanding into a red giant. Life on Earth, if any remains, will face challenges far beyond what a distant black hole merger could pose. Let's consider the ultimate fate of black holes in the far future of the universe. As we mentioned, Hawking radiation causes black holes to evaporate slowly. For stellar mass black holes, this takes an incomprehensibly long time. But wait long enough, and they will eventually fade away. In the incredibly distant future, after all stars have burned out, after even the longest-lived red dwarfs have cooled to black dwarfs, after protons themselves have potentially decayed, black holes will be among the last remaining structures in the universe. They'll sit in an expanding, cooling, darkening cosmos, occasionally flickering with Hawking radiation. Over timescales of 10 to the 100 years or more, even the supermassive black holes will evaporate completely. What's left after a black hole evaporates is uncertain, perhaps only a sparse gas of particles and radiation, spreading ever thinner as space expands. This is one possible end state of the universe, sometimes called the heat death. Maximum entropy, minimum structure, perfect equilibrium. But let's return to the present and to questions we can actually investigate. One active area of research involves finding intermediate mass black holes. These would bridge the gap between stellar mass and supermassive black holes. We've found hints of them in globular clusters, dense balls of stars orbiting galaxies. Some globular clusters show evidence of a central mass concentration that could be an intermediate mass black hole, but the evidence is often ambiguous. Another place to look is in dwarf galaxies, small galaxies that might host smaller supermassive black holes. Recent observations have found some dwarf galaxies with central black holes containing tens of thousands to millions of solar masses. Understanding how intermediate mass black holes form could help us understand how supermassive black holes grow. Are they built from mergers of stellar mass black holes? Do they form from the direct collapse of massive gas clouds? Both pathways might occur. Black holes also serve as natural laboratories for testing physics at its extremes. Near the event horizon, gravitational fields are strong, matter moves at relativistic speeds, and quantum effects become important. Observations of black holes let us test general relativity in regimes impossible to recreate on Earth. So far, general relativity has passed every test with flying colors. The observations match Einstein's century-old predictions with stunning precision. But scientists remain open to the possibility that at some level, in some extreme enough situation, deviations from general relativity might appear. Such deviations could point the way to a deeper theory, one that unifies gravity with the other forces of nature. This has been a holy grail of physics for decades. String theory and other approaches offer possibilities, but experimental evidence remains elusive. Black holes might also provide that evidence. Subtle deviations in gravitational wave signals or in the shadows of black hole images could reveal new physics. This is why scientists scrutinize the data so carefully, looking for even tiny departures from predictions. Let's think about the energy locked up in black hole rotation. A spinning black hole possesses enormous rotational energy. In principle, this energy could be extracted and used. Roger Penrose proposed one mechanism for doing so. The Penrose process involves dropping an object into the ergosphere, a region outside the event horizon where space-time is dragged along by the black hole's rotation. If the object splits into two pieces, with one piece falling into the black hole and the other escaping, the escaping piece can carry away more energy than the original object had. This energy comes from the black hole's rotation. The process slows the black hole's spin slightly while extracting energy. A sufficiently advanced civilization might use this to power itself, though the engineering challenges would be formidable. Another proposed mechanism is the Blandford-Znajek process, which could extract energy from a rotating black hole's magnetic field. This might be how some active galactic nuclei power their jets, though the details are still debated. Black holes can act as gravitational lenses, bending light from more distant objects. If a black hole passes in front of a background star, the star's light gets bent around the black hole, creating distorted, brightened images. By carefully measuring how background stars brighten and fade as a black hole passes in front, astronomers can detect black holes that aren't actively accreting matter and glowing. This technique has been used to find isolated stellar mass black holes drifting through our galaxy. The effects of gravitational lensing near a black hole can be quite dramatic. Light can orbit the black hole multiple times before escaping, creating multiple images of the same object at different distances from the black hole's shadow. Now, let's consider the paradoxes and puzzles black holes pose. They're boundaries between the known and the unknown, places where our theories reach their limits. They remind us how much we still have to learn about the universe. The resolution of the information paradox, for instance, might require a fundamental rethinking of how space-time and quantum mechanics fit together. Some physicists propose that information is somehow encoded on the event horizon itself in a holographic manner. The holographic principle suggests that all the information contained in a volume of space can be represented on the boundary of that volume. For a black hole, this would mean all the information about what fell in is encoded on the event horizon. This idea has far-reaching implications beyond black holes. It suggests that the three-dimensional universe we perceive might be a projection of information encoded on a two-dimensional surface. It's a strange and beautiful idea, still being explored. Black holes force us to confront questions about the nature of reality. What is space-time made of at the smallest scales? How do quantum mechanics and gravity fit together? What happens to information in extreme environments? Is there a limit to how much we can know about the universe? These questions have no easy answers. They're at the frontier of human knowledge. And black holes, those mysterious voids where stars go to die, are the keys to unlocking deeper understanding. As we observe more black holes, as our instruments become more sensitive, as our theories become more sophisticated, we inch closer to answers. Each gravitational wave detection, each new image, each careful measurement of an orbiting star adds another piece to the puzzle. The universe is revealing its secrets slowly, and black holes are among the most carefully guarded. They don't give up their mysteries easily, but persistence pays off. Human curiosity, ingenuity, and patience have brought us this far. Let's think for a moment about the sheer scale of what we're discussing. A supermassive black hole containing billions of solar masses, with an event horizon spanning billions of kilometers, sitting at the center of a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. And yet we've figured out how to study these objects. We've measured their masses, watched them orbit, detected the ripples they create in space-time, even captured their shadows in images. It's a testament to what science can achieve. The mathematics describing black holes is elegant. The Schwarzschild solution describing a non-rotating black hole is surprisingly simple given how strange the object it represents is. The Kerr solution for rotating black holes is more complex, but still remarkably beautiful. These mathematical solutions were discovered decades before we had any observational evidence that black holes actually exist. They emerged purely from following the logical implications of Einstein's equations. It's a stunning example of mathematics leading the way, predicting reality before we could observe it. Now imagine standing at a safe distance from a black hole, watching matter spiral in. The accretion disk glows brilliantly, heated to millions of degrees by friction. Jets of matter and energy shoot out perpendicular to the disk, traveling at nearly light speed. The black hole itself is invisible, a dark circle against the glowing background. But you can see its shadow, the region where light has been captured. Around the shadow, light from the accretion disk is bent and distorted, creating a bright ring. If the black hole is rotating rapidly, the ring appears brighter on one side because matter moving toward you on that side is relativistically boosted. The light appears brighter and bluer. Matter moving away on the other side appears dimmer and redder. Time itself runs at different rates at different distances from the black hole. A clock closer to the event horizon ticks more slowly than one farther away. If you had two synchronized clocks and dropped one toward the black hole while keeping the other, they'd quickly fall out of sync. This isn't an illusion or a trick. Time genuinely passes at different rates in different gravitational fields. It's been measured with precise atomic clocks at different altitudes on Earth. Near a black hole, the effect is extreme. Black holes remind us that the universe is stranger and more wonderful than everyday experience suggests. We live in a gentle gravitational environment where space-time is nearly flat. But the universe contains regions where space-time twists and curves dramatically, where the familiar rules no longer apply. And yet, the same physical laws govern both environments. The equations that describe how a ball falls on Earth also describe how matter falls into a black hole. It's just that near a black hole, we see those equations pushed to their limits. The universe is consistent even when it's strange. That consistency lets us make predictions, test theories, and gradually understand more It's one of the deepest insights of science. The universe plays by rules, and we can figure out what those rules are. Let's drift back to the question of whether anything can escape a black hole once it's crossed the event horizon. According to classical general relativity, the answer is no. The event horizon is a one-way boundary. Everything inside is drawn inexorably toward the singularity. But quantum mechanics complicates this picture. Virtual particles appearing near the event horizon can lead to Hawking radiation escaping. In a sense, this represents information from inside the black hole making its way out, though in a highly scrambled form. Whether the information is truly preserved or lost remains one of the biggest unsolved problems in theoretical physics. Hawking initially thought information was destroyed, violating quantum mechanics. Later, he changed his mind and proposed that information was preserved, though we don't yet understand how. This debate touches on fundamental questions about the nature of reality. Quantum mechanics says information is never truly lost. General relativity, in its classical form, says anything entering a black hole is gone forever. Something has to give. The resolution likely requires a quantum theory of gravity, which remains elusive. Various approaches exist, but none has achieved the level of experimental confirmation that general relativity and quantum mechanics individually have. Black holes sit at the intersection of these two great theories, highlighting where they come into tension. Resolving that tension is one of the grand challenges of 21st century physics. In the meantime, we can observe black holes, measure their properties, and test predictions we can make. We can watch stars orbit them, detect their mergers through gravitational waves, and image their shadows. Each observation teaches us something new. Consider how far we've come in a century. When Einstein published his theory of general relativity in 1915, black holes were purely theoretical. By the 1960 seconds and 70 seconds, astronomers had found the first strong candidates for black holes. By the 1990 seconds, we had compelling evidence for supermassive black holes at galactic centers. In 2015, we detected gravitational waves from merging black holes. In 2019, we saw the first image of a black hole shadow. The pace of discovery is accelerating as our technology improves. Future telescopes and detectors will reveal even more. Space-based gravitational wave detectors will observe the mergers of supermassive black holes. Next-generation imaging arrays might reveal more details about black hole shadows and the extreme environments around them. We might discover whether primordial black holes exist, whether they make up dark matter, and how the first supermassive black holes formed. We might find evidence for new physics in subtle deviations from general relativity's predictions. Or we might find that general relativity continues to hold up perfectly, which would be remarkable in its own right. Either way, we'll learn something profound about the universe. Let's imagine the future of black hole research. Astronomers will catalog more black holes, building a census of their masses, spins, and locations. This will tell us about how stars evolve, how galaxies form, and how the universe has changed over cosmic time. Gravitational wave astronomy is still in its infancy. As detectors become more sensitive and more are built around the world and in space, we'll detect fainter and more distant mergers. We might even detect the gravitational wave background, a faint hum from all the black hole mergers throughout cosmic history. Theoretical physicists will continue grappling with the paradoxes black holes pose. Each new idea, each new calculation, brings us closer to understanding how quantum mechanics and gravity fit together. The answer, when it comes, will likely be surprising and beautiful. And perhaps one day, far in the future, humans or their descendants might actually visit a black hole, not falling in, of course, but orbiting at a safe distance, studying it up close. The engineering challenges would be immense, but so were the challenges of reaching the moon once. Black holes have journeyed from mathematical curiosities to confirmed astronomical objects to subjects of cutting-edge research in just over a century. Who knows what the next century will bring? The universe is vast and full of wonders. Black holes are among the most extreme, most mysterious, most fascinating of those wonders. They challenge our understanding, inspire our imagination, and remind us how much remains to be discovered. As you drift off tonight, let yourself float among the stars. Picture the invisible dancers at galactic centers, the collapsed cores of dead stars, the ripples spreading through space-time from distant collisions. You're part of a universe that contains these marvels, a universe where matter and energy can be compressed to infinite density, where time flows at different rates, where space-time itself can be warped and twisted. It's a strange universe, but it's our universe. And every question we answer reveals new questions. Every mystery we solve points to deeper mysteries. The journey of discovery continues, always. And now we've come to the end of our journey through the cosmos, drifting past black holes and event horizons, through curved space-time and quantum mysteries. We've explored where gravity becomes so strong that even light cannot escape, where time itself slows and stops, where the universe reveals its most profound secrets. You are made of atoms forged in stars, some of which ended their lives in the cataclysmic collapses that create black holes. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in stellar furnaces, or in the violent explosions of dying stars. In a sense, you're connected to black holes through the very elements that make up your body. You're part of the same cosmic story, the same universe that contains both the gentlest whisper of starlight and the most extreme environments imaginable. So as you rest tonight, know that you carry the universe within you. Your thoughts are patterns of neurons firing, neurons made of atoms, atoms forged in stars. The line between you and the cosmos isn't as clear as it might seem. Let your breathing slow now. Let your thoughts grow soft and distant, like stars fading into morning light. Let yourself drift, untethered, into sleep. The mysteries will still be there tomorrow. The black holes will still be dancing at the centers of galaxies. The universe will continue its grand expansion, its slow evolution from simplicity to complexity and back again. But for now, you can rest. You've traveled far tonight, from Earth to the edge of the unknown. You've peered into the darkness and found wonders there. So close your eyes, let go, allow yourself to float in the gentle darkness of your own mind, as peaceful and as quiet as the space between the stars. Sleep well, and thank you for journeying with us through the greatest mysteries the universe has to offer. Good night. But before sleep takes you completely, let's linger a little longer in this cosmic space, exploring more of what makes black holes so endlessly fascinating. Think about the first person to conceive of something like a black hole. That was John Michael, an English clergyman and natural philosopher, back in 1783. He wondered what would happen if a star was so massive and dense that even light couldn't escape its gravitational pull. Michael's dark stars, as he called them, were based on Newton's theory of gravity and the idea that light consists of particles. He calculated that a star with the same density as the Sun but 500 times its radius would trap light. He was remarkably close to describing a black hole more than 2 centuries ago. But Michael's dark stars were forgotten, and the idea didn't resurface until Einstein's general relativity provided the proper framework. Just months after Einstein published his field equations in 1915, Karl Schwarzschild found the first exact solution while serving in the German army during World War I. Schwarzschild's solution described the space-time geometry around a spherical, non-rotating mass. When pushed to its logical extreme, when all the mass is compressed within a certain radius, it predicted a region from which nothing could escape. Schwarzschild himself didn't think such objects could exist in nature, For decades, physicists treated black holes as mathematical curiosities, pathological solutions to the equations that didn't correspond to anything real. Einstein himself wrote a paper in 1939 arguing that black holes couldn't form, but the universe had other ideas. In the 1,930 seconds, Subramanian Chandrasekhar calculated that there's a maximum mass for white dwarfs, about 1.4 solar masses. Above that limit, gravity overcomes electron degeneracy pressure, and the star must collapse further. Later, physicists determined there's also a maximum mass for neutron stars, about 2 to 3 solar masses, though the exact number is still uncertain. Above that limit, nothing can stop gravitational collapse. A black hole is inevitable. In the 1,960 seconds, astronomers discovered quasars, incredibly bright and distant objects. The only plausible explanation for their enormous energy output was matter falling into supermassive black holes. Suddenly, black holes weren't just mathematical possibilities. They were necessary to explain what we observed. Around the same time, astronomers found Cygnus X1, a powerful X-ray source in the constellation Cygnus. It appeared to be a binary system where a massive, invisible object was pulling material from a visible blue supergiant star. That invisible object was almost certainly a black hole. Stephen Hawking famously bet Kip Thorne that Cygnus X1 wasn't a black hole. He structured the bet so that if he lost, at least he'd have the consolation prize of a subscription to a magazine. As evidence mounted, Hawking conceded the bet in 1990. Cygnus X1 is now accepted as one of the best black hole candidates. Let's talk more about what happens inside an accretion disk. Material spiraling toward a black hole doesn't fall straight in. Conservation of angular momentum means it forms a rotating disk, much like water spiraling down a drain. Within the disk, particles collide and rub against each other, creating friction. This friction converts orbital energy into heat. The inner parts of the disk, moving faster and experiencing more friction, become incredibly hot millions of degrees. At these temperatures, the disk emits primarily in X-rays. That's why X-ray telescopes are so valuable for finding black holes. A bright X-ray source paired with a visible star often indicates a black hole pulling matter from its companion. The structure of an accretion disk is complex. The inner edge can extend very close to the event horizon, especially for rapidly rotating black holes. Near the event horizon, relativistic effects become important. Orbits precess, light is bent, and time dilation is extreme. Some of the most massive black holes we've found weren't in our own galaxy. They're in distant quasars and active galactic nuclei. One of the most massive known black holes sits at the center of the galaxy, Home 15A. It contains about 40 billion solar masses. To put that in perspective, that's more than 10,000 times the mass of Sagittarius A star at the center of our Milky Way. Its event horizon would span about 790 astronomical units, nearly 20 times the distance from the Sun to Neptune. How such enormous black holes formed is a major question in astrophysics. In the early universe, there wasn't enough time for them to grow from stellar mass black holes through accretion alone. They must have either started much more massive or grown extraordinarily quickly. One possibility is direct collapse black holes. In the early universe, under the right conditions, a massive cloud of gas might collapse directly into a black hole without forming a star first. This would create a black hole containing thousands or even millions of solar masses from the start. Another possibility involves supermassive stars, stars hundreds or thousands of times more massive than the Sunday. These could have existed in the early universe when gas had lower metallicity. If they collapsed, they'd create massive black hole seeds that could then grow. Dense star clusters might also contribute. In the crowded core of a cluster, Stellar collisions and mergers could build up an increasingly massive star that eventually collapses, or multiple stellar mass black holes in the cluster could merge. Most likely, several of these processes occurred, each contributing to the population of supermassive black holes we observe today. Different galaxies might have grown their central black holes through different pathways. Now, let's think about what we actually see when we look at a black hole's accretion disk. The material isn't moving in simple circles. It's turbulent, chaotic, threaded with magnetic fields that channel and accelerate the flow. Magnetic fields play a crucial role in accretion. They transfer angular momentum outward, allowing material to spiral inward toward the black hole. They also launch jets from near the poles of the accretion disk. These jets are among the most spectacular phenomena in the universe. They're narrow beams of matter and energy, traveling at 99% or more of the speed of light, extending for thousands or even millions of light years. Some jets are so long they dwarf the entire galaxy they emerge from. The mechanism powering jets isn't fully understood, but it likely involves the interaction between the black hole's spin, the accretion disk, and twisted magnetic fields. The Blandford-Znajek mechanism, proposed in 1977, suggests that energy is extracted from the black hole's rotation through magnetic field lines that thread the event horizon. Jets can have profound effects on their surroundings. They plow through intergalactic gas, creating giant lobes of hot plasma. They inject energy into the space between galaxies, affecting how gas cools and forms stars. In some cases, jets appear to point directly at Earth. We call these blazars. Because we're looking straight down the jet, the relativistic beaming effect makes them appear extremely bright. Blazars can vary in brightness dramatically over short timescales as conditions in the jet change. Let's drift to the concept of the photon sphere. This is a region just outside the event horizon where light can orbit the black hole. Photons moving tangentially at this distance will circle the black hole indefinitely, neither falling in nor escaping. For a non-rotating black hole, the photon sphere is at 1.5 times the Schwarzschild radius. For rotating black holes, the situation is more complex, and the photon sphere depends on the direction of the orbit relative to the black hole's spin. The photon sphere is important because it determines what we see when we look at a black hole. Light from inside the photon sphere spirals inward and is captured. Light from outside can escape. This creates the dark shadow we see in black hole images. The shadow is slightly larger than the event horizon itself because of this light-capturing region. For the black hole in M87, the shadow has a diameter of about 40 billion kilometers, even though the event horizon itself is somewhat smaller. Now imagine you're watching from a safe distance as an astronaut falls toward a black hole. From your perspective, as they approach the event horizon, they appear to slow down. Their clock ticks more and more slowly compared to yours. As they get closer and closer to the event horizon, the light from them becomes increasingly redshifted, shifting toward longer, redder wavelengths. Eventually, they fade from view, their image frozen at the event horizon, becoming dimmer and redder until you can no longer see them. From the astronaut's perspective, though, nothing special happens as they cross the event horizon. They don't notice passing through any boundary. For a supermassive black hole, the tidal forces at the event horizon might even be mild enough to survive. They'd see the outside universe blue shifted and appearing to speed up. Behind them, the event horizon would look like empty space. Ahead, the singularity awaits, though they'd only have a brief time before tidal forces became fatal. This difference in perspectives highlights the relativity of spacetime. There's no universal, objective now. Different observers experience time differently depending on their motion and the gravitational fields they're in. Black holes force us to take seriously the implications of relativity that might seem abstract in everyday life. Near a black hole, these effects become dramatic and unavoidable. Let's consider the jets we mentioned earlier in more detail. Observations show that jets remain collimated, staying narrow even over enormous distances. This is remarkable. Without some mechanism to keep them focused, they'd spread out and dissipate. Magnetic fields provide that collimation. The jet material is ionized plasma, and it's threaded with strong magnetic fields that act like invisible pipes, keeping the jet narrow. The details of how this works are still being studied. Jets can interact with the surrounding medium, creating shocks and hotspots where the jet slams into ambient gas. These shocks can emit radio waves, X-rays, and gamma rays. Some of the most energetic particles in the universe might be accelerated in these jet shocks. Cosmic rays, high-energy particles that constantly bombard Earth from space, might originate in part from black hole jets. When these particles strike Earth's atmosphere, they create cascades of secondary particles that we can detect. Now let's think about binary black hole systems before they merge. Two black holes orbiting each other create a fascinating gravitational environment. If a star passes through the system, it can be captured or ejected at high speed, slingshot by the combined gravitational field. The orbit of binary black holes decays over time as gravitational waves carry energy away. For black holes orbiting at large distances, this process is very slow, but as they get closer, it accelerates. The closer they are, the stronger the gravitational waves, and the faster the orbit decays. In the final seconds before merger, the two black holes are orbiting each other hundreds of times per second, impossibly fast for objects containing tens of solar masses. The power output in gravitational waves peaks at a value greater than all the light emitted by all the stars in the observable universe combined for just a fraction of a second. Then they merge. The ring-down phase follows, where the merged black hole settles into its final state, emitting gravitational waves that decay in amplitude and frequency like a struck bell ringing down. By analyzing the entire signal, the in-spiral, merger, and ring-down, scientists can extract remarkably detailed information. The masses of the original black holes, their spins, how they were oriented, the mass and spin of the final black hole, and the distance to the system. Each detection teaches us something new. Some mergers involve black holes with different masses, others with similar masses. Some involve rapidly spinning black holes, others slow spinners. This diversity tells us about the variety of ways black holes form and evolve. Gravitational wave detectors continue to improve. LIGO and Virgo have been joined by Kagra in Japan. Future detectors like the Einstein Telescope and Cosmic Explorer will be even more sensitive, detecting mergers from across the observable universe. Space-based detectors like LISA, the Laser Interferometer Space Antenna, will detect lower frequency gravitational waves from more massive black holes. LISA will observe the mergers of supermassive black holes, events so powerful they shake the entire universe. Let's think about what we've learned from gravitational wave detections about black hole populations. Before these detections, our knowledge of stellar mass black holes came primarily from X-ray binary systems, where a black hole accretes from a companion star. But X-ray binaries are a biased sample. They require the black hole to have a companion and to be actively accreting. Gravitational wave detections find black holes that are isolated or in binary systems with other black holes, giving us a more complete picture. We've learned that stellar mass black holes can be more massive than we previously thought. We've found black holes in the mass gap between neutron stars and black holes where we expected few objects. We've discovered that binary black holes merge frequently enough that we can detect several events per month. This has been a revolution in astronomy, comparable to when Galileo first pointed a telescope at the sky. We're observing the universe in an entirely new way, through space-time itself. Now imagine the environment around a supermassive black hole at a galactic center. It's not empty space. There are stars orbiting close by, some in eccentric orbits that bring them perilously close to the event horizon every few decades. There are clouds of gas and dust, some of which feed the accretion disk. There are magnetic fields, both from the accretion disk and from the surrounding galaxy. There might be smaller black holes or neutron stars in orbit around the supermassive black hole. This is a dynamic, chaotic environment. Stars can collide or be tidally disrupted by the black hole's gravity. Gas clouds can fall in, causing flares of radiation. The entire region is bathed in intense radiation from the accretion disk, and yet life exists in the Milky Way, including on Earth, just 26,000 light-years from Sagittarius A star. The black hole's influence extends throughout the galaxy, shaping its evolution. But at our distance, it poses no threat. Gravity weakens with distance, and we're far enough away to be safe. Let's talk about tidal disruption events. These occur when a star passes too close to a black hole. The gravitational force on the near side of the star is much stronger than on the far side. This tidal force stretches the star. If the star crosses the tidal disruption radius, the tidal force exceeds the star's self-gravity. The star is torn apart. Half the stellar material falls into the black hole while the other half is ejected at high velocity. The material falling in forms an accretion disk, producing a bright flare of radiation that can last for months or years. Astronomers have observed dozens of these tidal disruption events, providing opportunities to study otherwise dormant black holes. These events also let us test general relativity in strong field regimes and study the properties of stars. The details of how a star is disrupted depend on its internal structure, which in turn depends on its mass, composition, and evolutionary state. Now let's consider what primordial black holes, if they exist, might tell us. These would have formed in the very early universe, perhaps in the first fraction of a second after the Big Bang. The conditions then were hot and dense, with quantum fluctuations creating regions of varying density. If a region was dense enough, it could collapse directly into a black hole. Depending on when and how this happened, primordial black holes could have a wide range of masses, from microscopic to thousands of solar masses. If microscopic primordial black holes exist, they'd be evaporating now through Hawking radiation. The final moments of evaporation would release a burst of gamma rays. Searches for these bursts have found nothing, placing limits on the abundance of very small primordial black holes. Larger primordial black holes could make up some or all of dark matter. Dark matter is the invisible substance that makes up about 85% of the universe's matter. We know it exists because of its gravitational effects, but we don't know what it's made of. Most physicists think dark matter consists of exotic particles that don't interact with light, but primordial black holes are an alternative possibility. Recent studies suggest they can't make up all of dark matter, but they might contribute a fraction. The detection of gravitational waves from merging black holes has renewed interest in this idea. Some of the mergers might involve primordial black holes rather than black holes from collapsed stars. Distinguishing between these possibilities is an active area of research. Let's drift to the concept of naked singularities. In most black hole solutions, the singularity is hidden behind an event horizon. But some solutions to Einstein's equations allow for singularities without event horizons, naked singularities exposed to the external universe. Roger Penrose proposed the cosmic censorship conjecture, which states that naked singularities can't form from realistic initial conditions. The universe, in effect, censors singularities by always surrounding them with event horizons. But this remains a conjecture, not a proven theorem. Some theoretical scenarios suggest naked singularities might be possible under exotic conditions. If one were observed, it would revolutionize our understanding of gravity and spacetime. Naked singularities would allow us to observe the breakdown of general relativity directly. Unlike black holes, which hide their singularities behind event horizons, naked singularities would be visible. We could, in principle, watch physics breaking down in real time. Fortunately or unfortunately, depending on your perspective, we've never observed anything that looks like a naked singularity. The universe appears to respect cosmic censorship, at least so far as we can tell. Now think about the information that falls into a black hole. A book, for instance, contains information in the arrangement of molecules in its pages. If the book falls into a black hole, that information seems to be lost forever. But quantum mechanics forbids information destruction. Information can be scrambled, spread out, or hidden, but it must persist. This leads to the black hole information paradox we mentioned earlier. One proposed resolution is that information is somehow encoded on the event horizon in a holographic manner. The event horizon's area increases when things fall in, and perhaps the information is stored in the quantum states of the horizon itself. Another proposal involves firewalls. This suggests that the event horizon isn't smooth and harmless, but rather a wall of high-energy radiation that destroys anything crossing it. This would resolve the information paradox, but at the cost of contradicting other cherished principles of physics. Yet another idea is that black holes have additional internal structure we haven't accounted for. Quantum corrections might modify the classical picture in important ways, allowing information to escape gradually through Hawking radiation. The debate continues, with brilliant physicists on various sides. It's a beautiful example of how science works. Paradoxes and puzzles drive progress. They force us to question our assumptions and develop new ideas. Black holes serve as theoretical laboratories where different ideas about quantum gravity can be tested, at least mathematically. While we can't perform experiments on real black holes, we can check whether proposed theories are mathematically consistent and whether they resolve known paradoxes. Let's think about the role of black holes in galaxy formation. Observations show that the mass of a galaxy's central supermassive black hole correlates with properties of the galaxy, like the mass of its central bulge or the velocity dispersion of its stars. This suggests that galaxies and their black holes grow together, influencing each other. When a supermassive black hole is actively accreting and launching jets, it injects enormous energy into the surrounding gas. This heats the gas, preventing it from cooling and forming new stars. This negative feedback regulates star formation. Without it, galaxies would convert their gas into stars too quickly and end up looking very different from what we observe. The energy from active galactic nuclei helps shape galaxy evolution over cosmic time. Conversely, galaxy mergers can funnel gas toward the central black hole, triggering episodes of intense accretion. The black hole and the galaxy grow together in a kind of cosmic dance, each affecting the other's evolution. This co-evolution extends across cosmic history. In the early universe, quasars, powered by supermassive black holes, were common. As time went on and gas supplies dwindled, quasars became rarer. Today, most supermassive black holes are quiet, like Sagittarius A star, but occasionally, an influx of gas awakens them. They flare back to life, briefly becoming active galactic nuclei before settling back into quiescence. Over billions of years, galaxies alternate between active and quiet phases. Now let's consider what observations of distant black holes tell us about cosmic history. The most distant quasars we've observed existed when the universe was less than 1 billion years old. At that time, the first stars and galaxies were just forming. Yet these quasars are powered by supermassive black holes containing hundreds of millions or billions of solar masses. They must have grown extraordinarily rapidly in the early universe. Understanding how they achieved this is a major question. It might involve supermassive stars or direct collapsed black holes forming the seeds. It might involve continuous, rapid accretion under ideal conditions in the early universe, or it might involve a combination of factors we haven't fully accounted for. Each new discovery of a distant, early quasar refines our understanding. We're probing the universe's first billion years, an era when everything was hotter, denser, and more dynamic than today. Let's think about the ultimate fate of black holes again, but in more detail. Hawking radiation means black holes evaporate, but the process is incredibly slow. For a solar mass black hole, the evaporation time is about 10 to the 67 years. That's not just longer than the current age of the universe, it's trillions upon trillions of times longer. The universe would have to age to incomprehensible antiquity for even a single stellar mass black hole to evaporate completely. For supermassive black holes, the timescales are even longer. The black hole in M87 would take something like 10 to the 100 years to evaporate. That's a 1 followed by 100 zeros. There aren't enough particles in the observable universe to write that number out in full if you used 1 particle per digit. During most of that evaporation, the black hole would lose mass incredibly slowly. Only in the final moments would the process accelerate. As the black hole shrinks, its temperature increases. The Hawking radiation becomes more intense. In the final second, the black hole would release an enormous burst of energy as the last of its mass converts to radiation. Then nothing would remain except a faint spray of particles and photons spreading into the void. This is one possible distant future for every black hole in the universe. Stars will long since have burned out. Galaxies will have dispersed. Protons might have decayed. Black holes will be among the last complex structures, sitting in a cold, dark, expanding universe. They'll flicker occasionally with Hawking radiation, slowly shrinking over time scales that make billions of years seem like the blink of an eye. And then, one by one, they'll vanish, leaving nothing but faint echoes in an empty cosmos. It's a melancholy vision, but there's beauty in it too. The universe, having started in a hot, dense Big Bang, would end in cold, sparse equilibrium, maximum entropy, minimum structure, a peaceful cosmic sunset after eons of activity. But that's trillions upon trillions of years in the future. For now, in the universe's youth, black holes are active and dynamic. They shape galaxies, launch jets, and challenge our understanding of physics. Let's return to the present and think about how black holes affect their immediate environments. Stars near a galactic center's supermassive black hole experience strong tidal forces. Their orbits precess, changing orientation over time. Some stars have very eccentric orbits that bring them close to the black hole at perihelion. As they swing past, they're moving at tremendous speeds, up to a few % of light speed. The gravitational influence of the black hole dominates their motion. By tracking these stars over years and decades, astronomers map out the gravitational field and confirm it matches predictions for a supermassive black hole. This is one of the strongest pieces of evidence that these objects exist. In dense, stellar environments near a black hole, collisions between stars can occur. These collisions might build up more massive stars, which then collapse to form intermediate mass black holes. The central region of a galaxy can be a factory for black hole formation. Now think about what it means that we can detect gravitational waves from black hole mergers billions of light years away. These events are so violent, so energetic, that they literally shake spacetime across the entire universe. The waves travel outward at light speed, expanding like ripples on a pond. By the time they reach Earth, they've weakened to almost nothing. The strain they induce in spacetime is incredibly tiny, much smaller than the size of an atomic nucleus, yet we can detect them. This is a testament to human ingenuity and the precision of modern technology. LIGO and other detectors use laser interferometry to measure changes in distance smaller than anything we'd ever measured before. Each detection is a triumph, revealing events that occurred in the distant universe long before Earth even existed. We're observing cosmic history through ripples in space-time itself, and we're just getting started. As detectors improve and more come online, we'll observe fainter and more distant events. We'll build a complete picture of how black holes populate the universe, how they form, and how they evolve. Let's think about magnetars, the most magnetic objects in the universe. These are neutron stars with magnetic fields a quadrillion times stronger than Earth's. Some theories suggest that when two neutron stars merge, they might form a black hole surrounded by a powerful magnetic field. This magnetized black hole could power extraordinary phenomena, possibly including gamma-ray bursts, the most energetic explosions in the universe after the Big Bang itself. The details are still being worked out, but the connection between black holes and extreme magnetic fields is an active area of research. Black holes might also produce neutrinos, ghostly particles that barely interact with matter. When material accretes onto a black hole, nuclear reactions in the hot disk could produce neutrinos. Detecting these would provide another window into black hole physics. Neutrino detectors like IceCube in Antarctica are searching for high-energy neutrinos from astrophysical sources. Some might come from black holes and their accretion disks. Each detected neutrino could teach us something new about the extreme environments around black holes. Now imagine the computer simulations scientists use to model black holes. These simulations solve Einstein's equations on supercomputers, tracking how space-time curves around moving masses. They simulate accretion disks, jets, magnetic fields, and the merger of black holes. The simulations have become remarkably sophisticated, incorporating complex physics like magnetohydrodynamics, radiation transport, and even nuclear reactions. They can model everything from the formation of a black hole in a supernova to the merger of supermassive black holes. By comparing simulations to observations, scientists test their understanding. If the simulation matches what telescopes see, that's evidence the theoretical model is correct. If there are discrepancies, that points to missing physics or incorrect assumptions. This interplay between theory and observation drives progress. Each informs the other, creating a feedback loop that gradually refines our understanding. Let's drift to the idea of a multiverse. Some theories of quantum gravity suggest that the interior of a black hole might connect to another universe, completely separate from our own. This is highly speculative, but it's a tantalizing possibility. If true, black holes would be more than exotic objects in our universe. They'd be gateways to other realities, each with potentially different physical laws and constants. Our universe might itself be the interior of a black hole in some larger cosmos. These ideas push at the boundaries of science and philosophy. They're difficult or impossible to test with current technology, but they're worth contemplating as exercises in understanding what's possible within the framework of our theories. Science fiction has explored these ideas extensively, from wormholes to parallel universes. While most of these stories are fantasy, they're inspired by real physics. Black holes truly are gateways to the unknown, even if not in the literal sense fiction imagines. Now let's think about the sound of black holes. Gravitational waves are often described as ripples in spacetime, but they can also be thought of as a kind of sound, vibrations propagating through the fabric of the cosmos. Scientists have converted gravitational wave signals to audio frequencies humans can hear. The chirp of merging black holes sounds like a rising tone, a cosmic whistle that sweeps upward in pitch before cutting off abruptly. Each merger has a slightly different sound depending on the masses and spins of the black holes involved. Listening to these sounds, scientists can recognize patterns and anomalies that might be hard to spot in graphs and numbers. It's a reminder that science isn't just about cold equations. It's about finding creative ways to understand nature, whether through sight, sound, or abstract mathematics. Let's consider what black holes teach us about the limits of knowledge. The event horizon is more than a physical boundary. It's an epistemological one, a limit to what we can know. Information from beyond the horizon can never reach us. This raises philosophical questions. If there are facts about reality that we can never access, in what sense can we say we know the universe? Science has always dealt with the unknown. But black holes present unknowns that are in principle unknowable, at least from outside. Yet even these limits are informative. They tell us something deep about the nature of spacetime and causality. They reveal the structure of reality, even as they hide certain details from us. And perhaps quantum gravity will eventually reveal that the event horizon isn't quite as absolute a barrier as classical general relativity suggests. Information might leak out through Hawking radiation or other quantum effects. The unknowable might become knowable after all. Now, let's think about exotic black hole solutions. Physicists have discovered many different solutions to Einstein's equations, representing various types of black holes. Besides the familiar Schwarzschild and Kerr black holes, there are Reisner-Nordstrom charged black holes, Kerr-Newman charged and rotating black holes, and more. There are even solutions representing black holes in higher dimensions. If our universe has more than the familiar 3 spatial dimensions, perhaps curled up too small to see, black holes in those spaces could have very different properties. String theory, one approach to quantum gravity, suggests that space-time might have 10 or 11 dimensions. Most are compactified, rolled up into tiny structures. Black holes in this higher dimensional space could manifest in our 3-dimensional perception in unusual ways. These are theoretical possibilities, explored through mathematics. Whether nature actually makes use of them is an open question, but the very fact that the equations allow such diversity hints at the richness of possible realities. Let's drift back to observational astronomy and think about how we search for black holes. For isolated black holes not accreting matter, detection is challenging. They don't emit light, and they're small even though massive. One technique is microlensing. When a black hole passes in front of a more distant star, its gravity bends the star's light, briefly brightening it. By monitoring millions of stars and looking for these brightening events, astronomers can detect invisible compact objects. This method has found several candidate isolated black holes wandering through our galaxy. Combined with other observations, we're building a census of the galaxy's black hole population. Another approach is looking for the absence of light. If a black hole passes in front of a background nebula or star cluster, it would create a dark spot as it absorbs light. This requires high-resolution observations and careful analysis, but it's possible. As our observational techniques improve, we'll find more black holes and characterize them better. Each discovery adds to our understanding of how common black holes are and where they exist. Now imagine being an astronomer in the future, with technology far beyond what we have now. You might have gravitational wave detectors so sensitive they can observe black hole mergers anywhere in the observable universe. You might have imaging arrays that can resolve features on event horizons. You might even have ways to probe the quantum structure of spacetime near black holes, testing theories of quantum gravity directly. The black holes we observe now with such effort might be studied routinely, their properties cataloged and understood. Or perhaps you'd be an astronaut, piloting a spacecraft through the warped spacetime near a black hole, using its gravity to slingshot to another destination. Science fiction loves this idea, and while it's far beyond current technology, physics doesn't forbid it. The future is open, full of possibilities we can barely imagine. Black holes will be part of that future, continuing to challenge and inspire us as we reach deeper into the cosmos. Let's think about the poetry of black holes. They're objects where matter becomes invisible, where time stops, where space itself folds inward. They're the universe's deepest mysteries, its darkest secrets, yet they're made of the same fundamental stuff as everything else. A black hole is just matter and energy organized in an extreme way. It follows the same physical laws as a falling apple or an orbiting planet, just pushed to their limits. There's something profound about that. The universe is one, unified by physical law. From the smallest particle to the largest galaxy, from the gentlest breeze to the most violent explosion, the same principles apply. Black holes remind us of this unity. They show us what happens when familiar physics is pushed to extremes, and they hint that our current understanding, as good as it is still incomplete. The full story of black holes hasn't been written yet. We're still in the early chapters. Each observation, each theoretical advance, each new idea adds pages to the book. And you, drifting off to sleep with these cosmic wonders in your mind, are part of that story. Human curiosity about the universe drives all discovery. Your wonder, your questions, your imagination, they connect you to every scientist who has ever looked up at the stars and asked why. So rest now, knowing that the universe is vast and strange and beautiful, knowing that black holes dance at the centers of galaxies, knowing that space-time itself bends and flows under the weight of matter and energy. Let your thoughts drift like light near an event horizon, circling, spiraling, gradually slowing. Let the cosmic mysteries cradle you as you slip towards sleep. The black holes will still be there tomorrow, patient and eternal, waiting for us to unravel their secrets. But tonight, they're just companions in the darkness, fellow travelers through the cosmos. Sleep well, cosmic explorer. Rest peacefully among the stars. Before we part, let's linger just a little longer in the twilight between waking and dreaming, exploring a few more facets of these cosmic enigmas. Think about the scale of what we're discussing. The nearest known black hole to Earth, called Gaia BH1, is about 1,560 light-years away. Light from it, if it emitted any visible light, would take over 15 centuries to reach us. The light leaving that black hole's vicinity when medieval castles were being built in Europe is only just arriving at Earth now. And that's one of the closest. Most black holes we observe are thousands, millions, or even billions of light years away. When we detect gravitational waves from a merger, we're observing an event that happened in the deep past, perhaps before Earth even formed. Perhaps before our sun ignited. We're time travelers in a sense, looking back through cosmic history every time we observe a distant object. Astronomy is the study of the past, of light and gravitational waves that have journeyed across the universe to reach us. Let's consider the black holes we haven't found yet. Statistical estimates suggest the Milky Way contains about 100 million stellar mass black holes. We've confirmed only a few dozen. The vast majority remain invisible, drifting through space without companions, without accretion disks, producing no light. They're out there, though, silently orbiting the galactic center, along with ordinary stars. Occasionally, one might pass relatively close to our solar system, its presence betrayed only by a subtle gravitational influence on the orbits of distant comets. Every galaxy likely contains its own population of black holes. In the universe's observable volume, there might be trillions upon trillions of black holes. Each one is a laboratory of extreme physics, a window into the nature of space-time and gravity. Now think about the energy locked in rotating black holes. The Penrose process we mentioned could extract up to 29% of a black hole's rest mass energy. That's far more efficient than nuclear fusion, which converts less than 1% of mass to energy. A civilization advanced enough to harness this energy would have access to a nearly limitless power source. The black hole would spin down over time, but the total energy available would be enormous. This is the basis for some science fiction concepts of advanced civilizations. Of course, we're nowhere near this capability, but it's not forbidden by physics. In principle, the energy is there, waiting. Perhaps in some distant future, humanity or its descendants will tap into it. Let's drift to the question of whether black holes could be used for computation. The holographic principle suggests that information storage capacity scales with surface area, not volume. For a black hole, that means information could be stored on the event horizon. Theoretical calculations suggest a black hole might be the ultimate computer, capable of storing and processing information at the maximum rate allowed by physics. The Bekenstein bound sets a limit on how much information can be contained in a given volume of space, and black holes achieve this limit. Whether this theoretical capacity could ever be harnessed is another question. But it's fascinating to think that these engines of destruction might also be engines of computation, processing information at rates far beyond anything we can achieve with conventional computers. Now imagine the view from near a black hole. If you were in orbit at a safe distance, you'd see the rest of the universe distorted by gravitational lensing. Light from stars behind the black hole would be bent around it, creating multiple images. Directly behind the black hole, you'd see a bright Einstein ring, a circular halo of light from background sources. The black hole itself would appear as a dark disk, utterly black, absorbing all light that falls on it. If there's an accretion disk, it would glow brilliantly, perhaps brighter than 1,000 suns. The disk would appear asymmetric due to relativistic effects, one side brighter and bluer as material moves toward you, the other dimmer and redder as it moves away. If you were unfortunate enough to fall toward the black hole, your view would become increasingly distorted. The universe ahead would appear to expand and brighten as light is blue shifted. The universe behind would shrink and dim as light is red shifted. At the event horizon, your view would be split. Half the celestial sphere would show the outside universe, concentrated into a bright circle. The other half would be black, looking inward toward the singularity. And then you'd cross the horizon. In classical general relativity, you'd have a brief time before tidal forces became fatal. For a supermassive black hole, this could be seconds or even minutes. For a stellar mass black hole, it would be almost instantaneous. Let's think about the strangest black hole scenarios physics allows. In Einstein's equations, the inside of a rotating black hole contains a ring singularity rather than a point. The mathematics suggest that passing through this ring might lead to another region of spacetime. This is the origin of wormhole ideas. But the interior solutions are generally thought to be unstable and unphysical. Quantum effects not included in classical general relativity would probably prevent such exotic structures from forming. Still, the mathematics is beautiful. It hints that spacetime might be more flexible, more interconnected than we usually imagine. Even if wormholes don't exist, the fact that the equations allow them teaches us something about the nature of space and time. Black holes have also inspired new ways of thinking about information in thermodynamics. The realization that black holes have entropy proportional to the area of their event horizons was a major insight. This led to the holographic principle, which suggests that the information content of a volume of space is related to the area of its boundary, not its volume. This has profound implications for quantum gravity and might hint at the fundamental nature of space-time itself. Some physicists think space-time isn't fundamental but emergent, arising from more basic quantum information structures. If so, black holes, with their intimate connection between geometry and information, might be key to understanding this emergence. Now let's consider black holes in different cosmic environments. In the centers of dense globular clusters, multiple stellar mass black holes might exist in close proximity. They'd interact gravitationally, sometimes forming binaries that eventually merge. In galactic nuclei, the environment is even more extreme. Stars and black holes orbit the central supermassive black hole in a complex, chaotic dance. Interactions can fling objects out of the galaxy entirely or send them plunging into the central black hole. Galaxies themselves sometimes collide and merge. When this happens, their central supermassive black holes eventually sink to the center of the merged galaxy and form a binary. These supermassive black hole binaries are among the most energetic systems in the universe. Before they merge, they might be detectable through their effects on surrounding stars and gas. After merger, the resulting black hole might receive a kick from asymmetric gravitational wave emission, potentially ejecting it from the galaxy entirely if the kick is strong enough. Let's think about what we still don't know. Despite decades of study, black holes remain mysterious. We don't fully understand how supermassive black holes formed so early in cosmic history. We don't know exactly how jets are launched and collimated. We don't know what happens at the singularity. We don't know how to resolve the information paradox definitively. We don't know whether cosmic censorship always holds, whether primordial black holes exist, or whether black holes could be portals to other universes. Each of these unknowns is an opportunity for discovery. Science progresses by identifying what we don't know and systematically working to understand it. Black holes provide no shortage of such opportunities. The tools available to study black holes continue to improve. Next-generation gravitational wave detectors will observe mergers throughout cosmic history. Future space telescopes might image event horizons with higher resolution, revealing more details of the extreme environments around them. Theoretical progress continues as well. New approaches to quantum gravity, new insights from mathematics and information theory, new computational capabilities all contribute to our growing understanding. And perhaps one day, we'll have a complete theory of quantum gravity that explains black holes from first principles. We'll understand what happens at the singularity, how information is preserved, and how space-time emerges from quantum foundations. That day might be decades away, or it might be centuries. But each year brings us closer. Each observation, each calculation, each new idea adds to the edifice of knowledge we're building. Now, as the night deepens and your thoughts grow soft, remember that you're part of this grand endeavor. Every human who looks up at the stars and wonders, every person who asks questions about the nature of reality contributes to our collective understanding. The universe reveals itself to those who pay attention. Black holes, for all their mystery, are part of that revelation. They show us that reality is stranger and more wonderful than everyday experience suggests. They remind us that the cosmos operates on scales far beyond human intuition. Yet through mathematics, observation, and careful reasoning, we can understand even these most exotic objects. Let that thought comfort you as you drift towards sleep. The universe makes sense. It follows laws we can discover, and the boundary between the known and unknown is always moving, always expanding as human knowledge grows. Black holes, those enigmatic voids where stars collapse into darkness, are no longer completely mysterious. We've measured them, imaged them, detected their collisions. We've probed their properties and tested theories about their behavior. Much remains unknown, but much has been learned, and the journey of discovery continues, generation after generation, as we reach deeper into the cosmos and closer to fundamental truth. So rest now, cosmic traveler. Let the mysteries of black holes fade into the background of your consciousness. Let your breathing slow and deepen. Let your body relax completely, released from the day's tensions. You've journeyed through curved spacetime, past event horizons, through the formation and evolution of these cosmic monuments to gravity. You've contemplated questions at the edge of human knowledge. Now let those thoughts drift away like photons escaping from near a black hole, redshifting into invisibility. Let yourself sink into the gentle darkness of sleep, which holds no mysteries, only rest and renewal. Tomorrow the sun will rise, the stars will remain in their orbits, black holes will continue their patient dance at galactic centers, and you'll wake refreshed, ready for whatever the day brings. But tonight, you've traveled among the most extreme objects in the universe. You've touched the boundary of the known, you've peered into the heart of cosmic mysteries, and now it's time to rest. The universe will keep its secrets a little longer, the black holes will wait, discovery can resume tomorrow. Let your mind go quiet now. Let your thoughts become as calm and still as the space between galaxies. Let sleep take you gently into its embrace. You are safe. You are at rest. You are part of a universe, vast and ancient and beautiful, a universe that includes both the gentlest whisper of light and the most extreme collapse into darkness. Sleep well, stargazer. Dream of cosmic wonders, and wake ready to face a new day under the same sky that holds countless mysteries yet to be unraveled. Thank you for journeying through the cosmos with us tonight. Thank you for your curiosity, your attention, your willingness to contemplate the profound. May your sleep be deep and peaceful. Good night.